dies. Now I'm about to hop into some live contingency examples. We'll just work through a few questions. We discussed the different notations in the previous video, so let's get into it. So here I've given us a live table, x, lx, and dx, and now we have to calculate the following. So the first question is P55, which we should remember P55 means the probability of someone aged 55 surviving 1 year. And remember, KPX is equals to KLX. Okay, so here we've got P55, that is equals to L55 plus 1 over L55. That we're going to refer to the table. What? Nice, and you can just pop that in a calculator. And now Q54, it's the same thing, we're just plugging it into the formula, remember, QX. I have to check. Very simple. So Q54 is to D54 over L54 equals to 11 over 890. You can pop that in a calculator. What's this red thing? No idea. And now we've got 2Q54, so that's the probability that someone aged 54 will survive. No. The probability of someone aged 54 will die within 2 years. I always mix that up, but it's alright. So let's go. What we're going to do here is we're going to go L54 minus L56. All of this over L54, and that's equals to 8. Nice, and you can just pop that into a calculator. Now we get to the word problems. These ones can get a bit wordy, but nothing we can't handle. Let's hop into it. For the probability that a life aged 53 dies before they reach 56. Age 53 dies before. Okay, so all that this is 3Q53. Do you agree with me? That's a life aged 53 and they die before they reach 56. So that's they die within 3 years, which is that. So let's do that. And remember, to do for this one is L53 minus L56. 53. Nice. Next one. The proportion of lives that are alive at 53 and will die while they are 56. Proportion of lives that are alive at 53 and will die while they are 56. So firstly, we know that they are alive at 53, L53, and the proportion that we're looking for are the ones that will die while they are 56. So that's D56, and that's all that it is. Yeah. $900. And that's that. You can pop that in a calculator. And then here's another way that these type of questions could be asked. Write an expression for the probability of a person aged X surviving 5 years and then dying sometime in the next 2 years. So this person aged X is living 5 years, and then after the 5 years, he's going to die within 2 years. So we must make an expression. I can think of a few. I'll start with the most straightforward one that I'm sure you're also thinking of now. So someone aged X is surviving 5 years, but now they need to die within 2 years. So then this person is now aged X plus 5, and they are dying within 2 years. That should make some intuitive sense. But so this is one way of doing it. Another way that I can think of, we can go D So if you look at this, it's pretty much, if you would write out this, if you'd write it out in the formulas and stuff, you would also eventually get to this. So it's the people that dying at x plus 5 and then x plus 6. Just adding that over the people that are alive at Lx. And then the last one, which was probably the least obvious, is the we can consider the curtate life. That would look something like 5kx 7 plus 5. He's dying within 2 years, so that's excluded, but then we'll include that one. So remember that kx, we discussed that this is the curtate, it's the curtate future lifetime that someone can expect to live. So we want to write out an expression for this person who we are expecting to live 5 years, but then dying within 2 years. So we're including this because he has to live the 5 years, but then after the 5 years, he's dying within 2 years. So he's not going to reach x plus 7. He's going to die before that. And we couldn't put, you might be thinking maybe we could do, but we can't really do that. That's not right, because the EX, that's the one that you'll probably find on your table. That's the expected value of, remember we said KX is equals to expected value of, sorry. No. We said that EX is the expected value of KX, right? So you can't put the expected value into a probability statement about the random, like about the random variable itself, the random variable being kx, which is some whole number. It's a, because the quantitative future lifetime, it's in integers, whole year, the whole years that this person is alive, between 5 and 7. So back to this the second one that we wrote here, I think I can explain it a bit more. So the dx plus 5, all that implies that we're speaking about the people that die in x plus 5 years, right? Implying that this person has already survived the 5 years. So they're going to die between x plus 5 and x plus 6 years. They already survived the 5 years. And then dx plus 6 means that they survived 6 years, and now they're going to die within x plus 6 and x plus 7 years. So if there was a timeline, and then we had whatever x over there, there's going to be x plus 5, right? And we said that person aged x survives 5 years, so they survive till here, x plus 5, but now they die within 2 years. So somewhere between these two, somewhere here, they need to die. That's not nice, but yeah, that's what we're working with. So then this dx plus 5 means that we're dying somewhere here, and then this dx plus 6, we're dying somewhere there. And then we add them, which gives us that summation over the people that are alive at Lx to get the expression. And we have Alex in the denominator because this Alex, am I right? We're dealing with the people who survived X years in the question. So the probability of a person who survived X years, who aged X, so they already survived X years. So now they need to survive another 5 years and then die in the next 2 years. So we're dealing with all the people at Lx, survived the 5 years and then died, and then maybe another year and died before this time 7. Thanks, I hope that helped.